All right, we are ready to get started with section 6.2.2. We're going to prove some circle chord conjectures. The first conjecture we're going to prove is the chord central angle conjecture. So these are conjectures that we came up with last week, but now we're going to actually prove them. We're going to use a two-column format. The chord central angle conjecture states if two chords in a circle are congruent, then they determine two central angles that are congruent. You can see we have our given information listed here. The BA is congruent to CD, and we need to prove that angle BOA is congruent to angle DOC. So we'll start with the given information. We have segment BA is congruent to segment CD. That is given. Step 2, we're going to state the radii that are congruent to one another. Now, of course, all radii in a circle are congruent, but we have to match up corresponding sides of the triangles that we're eventually going to show are congruent. So let's say that segment BO is congruent to segment CO, and segment AO is congruent to segment DO. All radii of a circle are congruent. But notice I didn't just make one big long statement that all four were congruent to each other. I matched them up, right? Again, so that when we state our congruent triangles, we have corresponding parts matching up. Okay, so step 3 here, we can state that triangle BOA is congruent to triangle COD. Oh, triangle COD by side, 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 triangle congruency shortcut. Now we can state that angle BOA is congruent to angle DOC by CPCTC. So the second conjecture here is the chord arcs conjecture. And it states that if two chords in a circle are congruent, then their intercepted arcs are congruent. Again, we have the given information that BA is congruent to CD, and we need to prove that arc BA is congruent to arc CD. So we'll start with the given information. BA congruent to CD, given. From our last proof, chord central angle theorem now tells us that angle BOA is congruent to angle COD. That's the chord central angles theorem. So step 3, we're going to say the measure of angle BOA is equal to the measure of arc BA, and the measure of angle COD is equal to the measure of arc CD by the definition of arc measure. So we need to change our statement of congruency from step 2 to a statement of equality. By the definition of congruence. This will allow us to take the information in step 3 and substitute it into step 4. So the measure of angle BOA from step 3 equals the measure of arc BA. And the measure of angle COD equals the measure of arc CD. Substitution. Property of equality. So we finish off arc BA congruent to arc CD. Definition of congruence. So our last proof here is the perpendicular to a chord conjecture. It states the perpendicular from the center of a circle to a chord is the bisector of the chord. We have the given information written there. We have what we need to prove. And we have a nice diagram over there to work with also. So we're going to start with the given information here. And circle O, yeah, chord CD, okay. OR perpendicular to CD. OR perpendicular to CD, given. Now this is important because since OR is perpendicular to CD, that means that angle ORC and angle ORD are right angles by the definition of perpendicular. So since both of those are right angles, then we know that angle ORC is congruent to angle ORD because all right angles are congruent. Step 4, OR congruent to OR. Same segment or reflexive property of congruence. Step 5, OC congruent to OD. All radii of a circle are congruent. That leads us to triangle OCD is isosceles. Definition of isosceles triangle. Then we can state angle C congruent to angle D, isosceles triangle theorem. Now we're ready to state triangle ORC congruent to triangle ORD by angle, angle, side, triangle congruent shortcut. And since we know the triangles are congruent, we can state that CR is congruent to DR by CPCTC. And now we can state that OR bisects CD by definition of bisect.